from Lee University will talk on 10,000 ways to count a truncated tetrahedron.
All right, so let's get started. First off, we're going to be playing with mathematical building blocks to build a tetrahedral construction, and then we're going to truncate that tetrahedral construction and see what comes up. And last, there's a question that arises about the largest non-truncated tetrahedron number, and we'll be looking at that. So our first building block is a tetrahedron. It is a pyramid with a triangular base. For our purposes, a unit tetrahedron is an equilateral tetrahedron with edge length 1. So first we have the first tetrahedral construction, which is this green long tetrahedron. Our second building block is an octahedron. Using a unit tetrahedron and unit octahedron, we can construct tetrahedral constructions. And a tetrahedral construction is just by definition a larger equilateral tetrahedron. So we started with our lone green tetrahedron. We added 3 blue ones, and then this inner complement is actually an octahedron. And so this red shape, which is an octahedron, a unit octahedron, fits nicely right in there for our second tetrahedral construction. And then for edge length 3, all tetrahedral constructions of edge length 3 or greater, some unit tetrahedrons appear upside down relative to the first unit tetrahedron. And so we have that golden tetrahedron that's pointing relative down to the first tetrahedron, and that's caused by the inner complement of the 3 red octahedron that appear in the third layer. So this is the inner complement, and then I just removed the octahedron and the other blue tetrahedron to reveal that, and then we have the third tetrahedral construction. For all tetrahedral constructions, we can count the volumes based on the number of unit tetrahedrons and octahedrons. So I like to call this tetravolumes. A unit tetrahedron has 1 tetravolume, makes sense. And then based on volume equations, a unit octahedron will have 4 tetravolumes. And then so we can look at the sequence of this in this nice chart. We have in our first layer 1 upward pointing tetrahedron, 0 octahedron, 0 downward pointing for a total of 1. And then we have in the second layer 1 plus 2 plus 1, 1 unit octahedron times 4 for the tetravolumes for a total of 8 tetravolumes. This is really just the tetrahedral numbers. So upward pointing tetrahedral numbers are our first nth tetrahedral numbers. Then you have the unit octahedrons that are just shifted down by 1, so n minus 1. But then they're multiplied by 4. And then downward pointing is just n minus 2. So if we take the closed formula for those 3 layers, sum them together and simplify, we get that our tetravolumes in any layer is n cubed. With that understanding, we can start building any tetrahedral construction, and we can also define a new process called cutting. So the process of cutting is to remove a tetrahedral construction from a larger tetrahedral construction. This cutting process creates a truncated tetrahedron. And there's our first, just an arbitrary truncated tetrahedron. Notice it has 4 hexagonal faces and 4 triangular faces. So the rules of this cutting process is a construction must have edge length 3 or greater. The smallest possible cut is to remove a unit tetrahedron from each corner, notated as 1, 1, 1, 1. A cut may not reduce any side of the construction to 0, otherwise we wouldn't have a truncated tetrahedron. And for construction of edge length 3, a cut of 2, 1, 1, 1 would reduce 3 sides to 0. We can see this because you can take the largest number and the second largest number and add them together. If they're equal the edge length, you've cut too much. That's not an allowable cut. A construction of edge length 3 has 27 tetravolumes. Cutting away 1, 1, 1, 1 produces the first truncated tetrahedron number as 23, and that is the truncated tetrahedron. So moving up to edge length 4, that has 64 tetravolumes. Possible cuts are 1, 1, 1, 1, 2, 1, 1, 1, 1, 1, 1 removes 4 tetravolumes, as I mentioned earlier. 2, 1, 1, 1 removes 11 tetravolumes. These 2 cuts add 60 and 53 respectively to the set of truncated tetrahedron numbers. So this is the truncated tetrahedron with 60 tetravolumes, and then this is just rotated. It's the 53 rotated for perspective. So moving to more arbitrary numbers, this is the list of cuts. It is on the OEIS as A003327. And so a 100th layer tetrahedron could be cut by any of these cuts. That would be allowable. So then this is the sequence of truncated tetrahedron numbers. And what's important to notice here is that the gaps start out rather large, but then if we move down here, we have 1034 and 1035. There's a distance of 1 there. There's no gap at all. But then it goes to 1042, 1046. So it seems like the gaps are starting to get smaller. The question arises, is there a largest non-truncated tetrahedron number? There are several different methods for trying to find this number. And as an undergraduate, I ran into very new fields to me, and I got to learn a lot during this process. But as of right now, no method has revealed the largest non-truncated tetrahedron number. The first method that I tried was to return to a paper that had already been published. The paper was on using equilateral triangles to create equal angular hexagons. The author of that paper had published that the largest non-hexagon number is 84. But of course, I found this paper rather difficult to read. So I was very curious why 84, and to see why it was difficult to read, I have to ask, can anyone read German? The author was Ike Hurdle in this very German paper. The entire paper was in German, except the pictures. On page 5, he says a very German phrase. And according, with the help of Google Translate, I can say this roughly means, unfortunately, we lack here an elegant number-theoretic proof of the explicit specifying the set of numbers Z6. Z6 referring to hexagons. So I take this to mean that Ike does not have a analytic proof necessarily, but he used a more brute force method. And this is backed up by Ike continues with a chart of hexagons that shows 84 is the largest non-hexagon number. By his example, I returned to the program that I originally created to find the truncated tetrahedron numbers. Unfortunately, the fastest program that I could create was still not fast enough for the resources that I have. From this method, I did realize that this answer could be in the millions, and it will be past edge length 150, so definitely not near 84. I also tried to think of this as subsets. The question can also be expressed as coverage. If you translate the question, it becomes, after what point does n cubed minus a cubed plus b cubed plus c cubed plus d cubed cover the natural numbers? That question can also be stated as, after what point does this product a cubed plus b cubed plus c cubed plus d cubed cover the set of n cubed minus n minus 1 cubed? Because you're allowed to keep cuts as you move up into layers. That question is dependent upon predicting unique values for the product of a cubed plus b cubed plus c cubed plus d cubed, which I have been unable to do. After writing out this product and taking linear algebra, I presumed the null space of this matrix would find the answer. It is true to say that the non-truncated tetrahedron numbers are the null space of the set of vectors that truncate a tetrahedron, but the wall of this method is that the linear algebra techniques assume real scalar multiplication. This non-truncated tetrahedron problem needs a technique that can assume integer scalar multiplication. And a wonderful definition from Wolfram Math World is Diophantine equations is an equation in which only integer solutions are allowed. So this seems to be like exactly what I'm looking for. With a set of linear equations, it should be possible to set up a series of Diophantine equations. Currently, this method seems the most promising, but finding instructions on these techniques has been limited. And this method, if it could be discovered, could work for an analytic proof of the hexagon numbers, and it could also work on some of the tiling problems that me and my friends are working at the university. So, I will leave you with a wonderful quote that says, "I have not failed, I've just found 10,000 ways that won't work." Are there any questions?
Well, just that one of the students that I worked with, though he didn't get to any conclusion, he believed that a small 2, 3, 4, 7 number of affine equations might allow one to construct all of the hexagon numbers.
Okay.
But we didn't quite finish that. But that might be worth looking at, actually, to see if you can make it work for the hexagon numbers using a small number of affine equations.
So all these techniques, I was definitely hoping to work with the hexagon numbers first as sort of like a practice room or a playground, and then bump them up into third dimension to find a much bigger number, a much bigger result. So,
Other questions?
yeah.
More just a comment, just my experience, it was really interesting looking into Pell equations as a variation. Pell's equations is
Pell's
on
equations.
variation on the Dow phantoms. They produce a lot of really interesting structures. So maybe not directly related to what you're working on,
But still very interesting. Okay.
Yeah.
I'll have to look that up.
All right, let us thank our speaker.